Hello Math 112 students. We are looking at Chapter 3 assignment questions after the first 10 questions. So we did the first 10 questions, we did those concepts in class. So we're just looking in this video at the back part of this assignment. So let's just read question 11. Use ordinary division of polynomials to find the quotient and remainder when the first polynomial is divided by the second. So what we're doing here is polynomial division. All right, there's something called long division of polynomials, and there's something called synthetic division of polynomials. We're only going to do synthetic division. We won't cover long division in this course. All right, synthetic division is a lot simpler, easier, faster. So synthetic division. All right, so what we do for synthetic division is we take the coefficients of the polynomial, and we put them in a box with one caveat. The coefficients of the polynomial have to go in a particular standard order. It has to, whatever the leading term is. So in this case, the leading term is the negative 4w to the third. The leading term is the term that has the highest exponent on the variable. Whatever that leading term is, whatever that exponent is, it has to step down by one number in the exponent with every step. And if it doesn't, then you have to put in what's called a placeholder. All right, a placeholder. So notice this goes w to the third and then w to the second, and then there is no w to the first, and then there's a constant, in other words, a w to the 0. So there's a w to the first term that is, I guess you could call it missing, and we're going to have to put something in its place. So we could treat this as if it's negative 4w to the third plus 5w squared plus 0w minus 8. And that's the same thing because 0w doesn't change anything. So now we're going to put these coefficients in the inside of a box. Negative 4, 5, 0, negative 8. And I'm putting them in a box. So this 0, that's what's called a placeholder. All right, and then I take what I'm dividing by. I'm dividing by w minus 3, and you're going to set that equal to 0 and solve it. So what do I get? W equals positive 3. This is the number I'm putting outside of the box. I'm putting a positive 3 outside of the box. How did I get that? I take the thing I'm dividing by, and I set it equal to 0, and I solve it, and that little solution is the number that I put outside the box. Okay, then this technique of synthetic division is going to happen, and it's basically 2 steps, 2 repeated steps. All right, add down, then multiply across, and then just repeat that. Repeat to the end. So here's what I mean by those steps. Add down. What I mean by that is inside this box, I'm going to take the first number in the box, the negative 4, and I'm going to add down. That means I add anything below it. Now there's nothing below the negative 4, so negative 4 plus nothing is negative 4. And I write that down below the box. Negative 4 plus nothing is negative 4. That's always going to happen with the first number in the box because nothing is going to be below it. It's just going to come down as it is. Then step 2, multiply across. What I mean by that is I take the 3 that's outside the box on the left, I multiply it by the negative 4 that's down here below the box, and I write it below the next number. So I'm multiplying the 3 by the negative 4, and I'm writing it below the next number. So I'm multiplying across here. 3 times negative 4 is negative 12. And then I repeat that same process. Add down. What I mean by that is take the 5, add it with what's below it, the negative 12. 5 plus negative 12 is negative 7. Then I do the second step again. Multiply across. I take the 3 that's out here on the left, multiply it by the last number I wrote down here below the box, and write it below the next number. 3 times negative 7 is negative 21. And you continue on with that process. 0 plus negative 21 is negative 21. 3 times negative 21 is negative 63. Negative 8 plus negative 63 is negative 71. And basically the process is over. Okay, now I just got to take what I've got down here and interpret that as the answer that the problem is asking me about. Okay, so what is the problem asking me? It's saying find the quotient and remainder. Okay, so how do I get the quotient? In other words, what's the answer that this thing is telling me? Okay, the answer here, these are going to be the new coefficients for the answer. The answer is always going to start 1 degree less than the problem started with. So we started with a w to the third, so my answer is going to start as w to the second. So it's negative 4 w to the second. And it's just going to walk down the exponents. Minus 7 w to the first, minus 21 w to the 0. And this number right here, the last number, is always the remainder. Always. That last number is always the remainder. Here's what you do with the remainder. You say plus, and you put that remainder over the thing you were dividing by. So over w minus 3. And this is the full answer to this division problem. We've just divided the polynomials. What that means is if I take the w minus 3 and multiply it by negative 4w squared minus 7w minus 21 plus negative 71 over w minus 3, I will end up with this polynomial here that I divided into. Alrighty, so let's see if I can type that answer in the way it wants me to. The quotient is, I gotta go back to my negative 4w squared minus 7w minus 21. The quotient is negative 4w squared minus 7w minus 21. I don't remember if that's right. I'm just trying to remember what I wrote, but I can't remember it. That is correct. And then the remainder is negative 71. That is the right answer. So that's how you type your answer in for that problem. That's called what? That's called synthetic division. It's a particular technique to divide polynomials. It works a lot of the time, but it doesn't work every time, which is why there's also a technique called polynomial long division that works every time. But it's going to work for the purposes of our class. It'll work. That's all we need to learn for this class. All right, again, use synthetic division to find the quotient and remainder when the first polynomial is divided by the second. Okay, so let's just go through this as another example. We put the coefficients of that in a box. That's going to be 1, negative 2, and 2. I did not need any placeholders because it walked down by 1 every time. C to the second, C to the first, C to the 0. And here I'm going to put negative 1 outside the box because that's what I would get if I solved this. If if I set it equal to 0 and solved it. Okay, then I go through my process. I add down, 1 plus nothing is 1. I multiply across, negative 1 times 1 is negative 1. I add down, negative 2 plus negative 1 is negative 3. I multiply across, negative 1 times negative 3 is 3. I add down, 2 plus 3 is 5. So what is my answer? Remember, my answer here always starts one less degree than the polynomial that I started with, which is a c to the second. So this is going to start as c to the first, 1c to the first. I can just put it as c minus 3, c to the 0, and then that's the what? This here is the remainder. So plus 5 over c plus 1. But all you have to do here is type this part into there, and just type the 5 into there for the remainder. Next, we have a problem that is going through the concept of the rational root theorem. The rational root theorem. Sorry for the bad handwriting here. Rational root theorem, also known, or the rational zero theorem. Same thing, roots and zeros. That theorem takes us through a way to find all of the rational roots of any polynomial function. So it basically helps us to solve almost any polynomial function. The rational roots theorem starts like this. All right. If you have a polynomial, p of x equals ax to the n plus bx to the n minus 1 plus cx to the n minus 2, all the way down to, let's say, I don't know, gx to the first plus h. All of the rational roots, all rational roots will take the form the factors of the constant term at the end, which I'm going to call h, divided by the factors of the leading coefficient, which I'm going to call a. And these can all be plus or minus. So in other words, you take the factors of the constant at the end, every factor of the constant, and put it over every factor of the leading coefficient, and that will give you all of the possible rational roots. It doesn't mean that all of them are rational roots. It means that all of them, every rational root of the function will be in the set that you just created by doing this. So let's finish that out for this problem. So my constant is negative 10. My leading coefficient is 33. So what are all the factors of 33? 1 and 33, 3 and 11. And I think that's it. Constants. The factors of 10 would be, and it doesn't matter that it's negative because any of these can be positive or plus or minus anyway. So 1 and 10, 2 and 5. So I'm going to put each one of these over each one of these. So first, I'm going to do the 1, right? The 1 over each of these 4. So 1 over 1, 1 over 33, 1 over 3, 1 over 11. Then I'm going to do the 10 over each of these 4. 10 over 1, 10 over 33, 10 over 3, 10 over 11. Then I'm going to do the 2 the same way. Let's write it down here. 2 over 1, 2 over 33, 2 over 3, 2 over 11, 5 over 1, 5 over 33, 5 over 3, 5 over 11. And then I kind of eliminate, if I have any repeaters, I might have some, I'm going to simplify any fractions, and if I have any that are kind of a repeat of any that came before it, I'm going to eliminate those. So 1 over 1, that's 1. 1 over 33. 1 over 3. 1 over 11. 10 over 1, that's just 10. 10 over 33. 10 over 3. 10 over 11. 2 over 1, that's 2. 2 over 33. 2 over 3. 2 over 11. 5 over 1, that's just 5. 5 over 33. 5 over 3. 5 over 11. And any of these can be plus or minus. So let's see what answer corresponds to what we just said. 10 over 30, 10 over 11, 10 over 3, 10. A looks good, except it doesn't put plus or minus in front of all of them, so A is wrong. 10 over 33, 10 over 11, 10 over 3. B looks really good. C is wrong. C's basically got them all flipped. The C, the answer choice C is wrong. It put all of the factors of 33 over all the factors of 10 instead of the way it should have been, which is the factors of 10 over the factors of 33. So B is the right answer there. And again, the whole point of that is that any of the rational roots, rational meaning any number that can be written as a fraction, like not a decimal that never ends and never repeats, any of the rational numbers that are zeros or roots of this polynomial will be in this set. These are the possibilities for the rational roots. Not all these are the rational roots of this polynomial, but these tell us what is possible for the rational roots. Okay, so that brings us to this problem where we are told, finally, this is kind of the gist, the point of the synthetic division and the point of the rational root theorem and finding the possible rational roots is to be able to solve, to be able to find all of the zeros of a polynomial function. And so we have this function, and we need to solve it. I'm going to try to show you a few different ways to go about this. All right, one way is to do the rational root theorem. So what are the possible rational roots? Well, our leading coefficient is 1. Our constant is 35. So the factors of 1 are just 1 in itself. The factors of 35 are 1 and 35, 5 and 7. So we put all of these over this one. So it's just 1 over 1, 35 over 1, 5 over 1, and 7 over 1. And all these can be positive or negative. 1, 35, 5, and 7. And so what we do is with synthetic division, we put 1, negative 3, negative 33, and 35 in the box, and we try these values to see which one works. We try these outside the box. Usually you're going to find one that works within the first 3 or 4 tries. So I would try the easiest ones first. I would try 1. Let's see if that works. 1 plus 0 is 1. 1 times 1 is 1. Negative 3 plus 1 is negative 2. 1 times negative 2 is negative 2. Negative 33 plus negative 2 is negative 35. 1 times negative 35 is negative 35. And that actually worked the very first time. How do we know it worked? Because we got a remainder of 0. When we get a remainder of 0, it means that it means that the factor x minus 1 divided into that evenly, perfectly, with no remainder, which means x minus 1 is a factor of this polynomial. And so if I set that equal to 0, that means I get x equals 1 as one of my zeros. Okay, so if I'm solving this, one of my zeros is 1. I already know that already, but I'm not done. I need to get, how many zeros do I need to get in all? Since I'm finding the real and imaginary zeros, the total number of zeros is always going to be equal to the degree. So I've got to find 3 total zeros, real and imaginary. So I take what's left here. What's left? What is the polynomial that's left after I've divided out this factor? Remember, it starts one less degree than what we started with, so that's the x to the third. So this is going to be 1x to the second minus 2x minus 35. And then we solve this. Once we get it down to a quadratic, we know we've got it whipped. We can do it because we can solve a quadratic. We've been doing this for years now, right? You can solve it by factoring. You can solve it by the quadratic formula. It's going to work somehow. I think we can factor this. This is going to factor as x minus 7. I prefer factoring if possible. What just happened here? All right. This factors as x minus 7 and x plus 5. And so my other zeros are 7 and negative 5. So all three of my zeros are 1, 7, and negative 5. They're all real numbers. I don't have any imaginary zeros. So 1, 7, and negative 5 are my answers. Let me go back to this problem again. There may be, I wanted to show you that there may be some simpler ways, some smarter ways to figure out what goes outside the box than just trial and error. One way is by your calculator. If you go to your calculator, here are some options for you. All right, hopefully you can see that. We could graph this function. If I can remember what it was, I believe it was, I can't remember, let me look back at it. X to the third minus 3x squared minus 33x plus 35. Okay. All right, I have this in the y equals part of my calculator. I hit graph. I know that's not showing up too well, is it? Hopefully you're seeing it enough. And what I do is I find the zeros that way, and I can kind of just look at it and tell. I may not even, I can find the exact value of the zeros by hitting second calc, option 2. And then let's say if I wanted to find this 0 over here, I'm clicking to the left until I finally see that thing pop up in my screen. Left bound, I want this blinky thing to be to the left of this point that I'm trying to find. So I click to the left and I know it's to the left of that point. I hit enter. Now it says right bound, I want the blinky thing to be to the right of that point. So I click to the right and I know it's to the right of that point. Now I click enter. Then it says guess, and I can bring my little blinky thing close to the point that I think it is and hit enter. And now it tells me that the answer is negative 5, 0. So negative 5 is one of my zeros. So I know that I could have used negative 5 and it would have worked outside of this box. Now what did we use? I think we used 1, and so you can use different numbers outside of the box. You can use, and it can still work. Any of the zeros that we use outside of here will work, and we'll get a remainder of 0, and then we'll end up with a polynomial that we can still go forward with. Let me just show you how that could have worked. If we'd have chosen negative 5, 1, negative 5, negative 8, 40, 7, negative 35, 0. And we would have ended up with that. So negative 5 worked because we got a remainder of 0, and we get x squared minus 8x plus 7 as the polynomial that's left. We factor that as x minus 7, x minus 1, and we still get x equals negative 5, positive 7, and positive 1 as the answers. So there's multiple ways you can go about this. Let me show you another way you could kind of figure out what goes outside the box in your calculator. So we could, see any of these zeros that would have worked right here. Right, -5 would have worked, 1 or 7. I can also go to the apps and go to Polynomial, and I can type in Polynomial Root Finder. And this actually, so the order would be 3, might be a way to do the problem completely. Some problems, especially if all the zeros are just nice whole numbers or integers, this could be a way to get the whole answer. But sometimes when the answers are like kind of strange, like if they're irrational answers or if they're complex number answers or something like that, then this may only get you part of the way to the answer that you have to get. You could just let it give you the real numbers, or you could let it give you the real and imaginary by clicking that. Or I don't care if it's a decimal or automatic. I don't care. I want it to be normal. I want it to be a float. This part doesn't matter unless we were doing trig. I click next by clicking the button below next. I can click graph. That's the button below next. I type in my coefficients, which are 1. What was the next one? Having trouble remembering. -3, -33, and 35. -3, -33, and 35. I believe that was right. Let me make sure. -3, -33, 35. Yeah. All right, and then I click solve, to click solve, I got to do the button below solve, which is graph. And it tells me all of the answers, 7, -5, and 1. Let's just say if this was one where 7 was one of the answers, but the other 2 answers were very strange answers that were like decimals that went on and on and on. And Math Excel wanted us to give an exact answer, not as a rounded off decimal, but as a radical. What we could do is just use the rational number answer that it gave us outside the box to get down to a quadratic equation, and then solve that quadratic equation in one of those ways that we know, either square root method or factoring or quadratic formula. All right, next problem. Okay, I'm gonna just try doing this in the app right off the bat, and see if we can just get the answers quickly that way. I think it's probably going to work since I'm looking at what kind of answers it's going to be. So I go to the app. Let me slide this down a little bit. All right, I go back to main so that I can start over, Polynomial Root Finder. All that looks good. All right, this time it's 1, enter, 8, enter, 21, enter, 20, enter. And I hit solve. And it looks like, did I enter it right? No, I did not enter it right at all. Let's go back to the coefficients. Somehow that did not enter right. 1, enter. 8, enter. 21, enter. 20, enter. Now it should give me the right answers. And yeah, here are the right answers. -4 and -2 plus or minus I. So that's a quick way to do some problems. -4 and -2 plus or minus I. Choice C would be the right answer there. All right, I went ahead on to number 18. Some of the others before that were just kind of repeated concepts that we've already done. This one's got a little higher degree, W to the 4th. So let's go to the app and see what happens when we type it in. Okay, so we are going to start out by putting this in the app. So we are not order 3 anymore, we are in order 4, so I'm changing that to 4. Once you change it to 4, this app no longer has the ability to just do the real solutions. It's going to do the real and imaginary solutions. It also doesn't, it's going to have to give you the answers as a decimal. It won't do them as a fraction. Let's go ahead and go to next. Also, when you jump up to a 4th degree, it kind of changes the format of how you put the coefficients in. So before it looked kind of intuitive how to do it, but now basically you're putting in the A4 spot, you're putting the coefficient of the x to the 4th, or in this case w to the 4th coefficient. You're putting the coefficient to the w to the 3rd. Here you're putting the coefficient for the w to the 2nd, and so on and so forth. So for this problem, we're putting a 1 for the w to the 4th, a -1 for w to the 3rd, a -5 for w to the 2nd, a -1 for the w, and a +6 for the, should have been a -6, a -6 for the constant, which is the a to the 0, a sub 0. Then we click solve, and it gives me these answers: 3, -2. Now, this is, let me tell you, this is a strange way that the calculator does these answers. 6.5 e -14. So 6.5 e -14 plus 1i. What does that mean? What does that 6.5 e -14 mean? E -14 means times 10 to the -14th power. So this is 6.5 times 10 to the -14th power plus 1i, or plus I. That means that we move the decimal point 14 places to the left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 6, 5 plus I. Here's the deal. This is so close to 0. It actually is 0. It's just that the calculator, for some reason, I don't know what's going on in the program of this calculator to make this the case, but a lot of times the calculator cannot bring itself to just say 0. So it puts some number really close to 0 on there when it's really just 0. So when you see something like 6.5 e -14, that's really just 0. So this is really just 0 plus 1i. So if I'm looking at these answers, this is really, the answers are 3, -2, 1i, and -1i. So 3, -2, and plus or minus I. Those are the answers. All right, we are looking now at a word problem number 19, P of T. This is the parts per million concentration of a particular drug in a patient's bloodstream, and it's going to be modeled by this function, where T is hours after the administration of the drug. So we're told now, it gives us the graph. It says use the formula to determine when the drug will be totally eliminated from the bloodstream. The good thing is we're looking at the graph, and we can just use the graph to tell us that. When is the drug totally eliminated? After 4 hours. You can see that the concentration of the drug in the bloodstream goes up. It reaches a peak somewhere right here around 2 hours, up to about 100 and maybe 190 or something like that parts per million, and then it goes up. It declines until it gets back to 0 in 4 hours. So we're going to put in 0. I'm sorry, we're going to put in 4. Part B, use the graph to estimate the maximum concentration of the drug. Round to the nearest integer as needed. Maybe we should look at this a little bit more closely. It's at 160, that would be 180, and then 200. So I'm thinking this is like maybe a little less than 190, right? So 190 would be halfway between this height and this height. So I'm thinking like maybe 187. I'm going to try that and just see. If it's not right, I may have to go to the calculator to do some more precise calculation. Let's try 187, see if that works. It worked. So good deal. Maybe we don't have to be that precise with an answer. Use the graph to estimate the time at which the maximum concentration occurs. We've already said that's 2 hours, the 2 hour mark. Use the graph to estimate the amount of time for which the concentration is above 140 parts per million. When is it above 140? Well, 140 is this height, and we are above that height once we get past 1 all the way until we get to 3. It says rounds to the nearest integer, so between 1 and 3 hours. Approximate amount of time for which the concentration, so that would be 2 hours. Between 1 and 3 hours, that means 2 hours total. The amount of time for which the concentration is above 140 is 2 hours. All right, so this word problem. The height of a box containing a certain printer cartridge is 1 inch more than the width, and the length is 7 inches more than the width. The volume of the box is 120 cubic inches. Then what are the dimensions of the box? What I can do, since it gives me the height and the length in terms of the width, I'm just going to say, the h is w plus 1, so 1 inch more than the width. The length is w plus 7, so 7 inches more than the width, and the width is just the width. So now I have everything in terms of w. So the volume of a box is length times width times height. So let's just say it's w times w plus 7 times w plus 1. That's width times length times height. And that whole thing equals the volume. And the volume is this, 120. And it asks for the dimensions of the box. So I can use this equation to solve for w. Okay, from here we have several options. We could, for instance, we could type the whole left side into y1, type the right side into y2, and find where they cross. We could go ahead and expand everything, which is what I'm going to do. I'm going to expand this. This is going to be, that's going to be w squared. I'm multiplying the w plus 7 and the w plus 1. That's w squared plus 1w plus 7w, so that's plus 8w plus 7. And then multiply that by the other w, and that's going to be w to the third plus 8w squared plus 7w, and I'm going to go ahead and move my 120 over, minus 120. So there's my volume function. Volume as a function of the width. And what I could do is I could do my polynomial root finder. I could put this in the app. That might be the easiest, kind of simplest way to do it. So I'm going to do that. All right, when I put it in the app, it gave me 3 as one of the answers, and then it gave me like negative 11 halves plus or minus 3.122i as the other answers. So since this is a real life context of a problem that's talking about the width of a box, I know that the imaginary answers are not going to be relevant to that real life application as far as the width of a box is concerned. So 3 is the answer I'm going for there. So if the width is 3, then the length is going to be 3 plus 7, which is 10, and the height is going to be 3 plus 1, which is 4. So there are the dimensions, and I can just type that into here to get the right answer. All right, this next problem, problem number 21, brings on kind of some different concepts than we've covered so far. If x minus c occurs k times in the complete factorization of the polynomial p of x, then c is a root of p of x equals 0 with what? With what? So what's going on here is there's this concept that when you factor a polynomial, let's say you have x minus 3, x minus 3, x plus 1, x plus 1, x plus 1, x minus 5. And it factors out that way when you factor it out completely. And we're able to factor it out completely, and that's the way it happens. Let's just pretend that's the case. So that means that another way we could write that is x minus 3 to the second, x plus 1 to the third, x minus 5. So however many times the factor shows up, that's called the multiplicity of that factor. The answer, in fact, the answer to this question is with multiplicity k. That's going to be in the drop-down box. So 3, x equals 3, is a solution with a multiplicity 2. X equals negative 1 is a root with a multiplicity 3. X equals 5 is a root with multiplicity 1. And the multiplicity tells you, the main thing that it does, it tells you something about what happens to the graph at that root. Like a root or a 0 is where the graph does something with the x-axis. It either crosses or it touches. It either crosses or touches. When I say touches, I guess I mean to say that it hits it but doesn't cross it. It touches it and then goes the other way. Or some people say it bounces right there. So it crosses when the multiplicity is odd. And it touches when the multiplicity is even. So that means that for x equals 3, it just touches the x-axis there. But for x equals negative 1 and 5, it crosses. So if I were drawing the graph, okay, if I were drawing this graph, that means that it would cross at 5. It would cross at negative. It would cross at. It would touch at 3. So let me draw that a little bit better. It would cross at 5. It would only touch at 3. Okay, touch and go the other way, and then it would cross again at negative 1. So I would know at least that much about my graph. Okay, so that's what the multiplicity is about. Okay, the next question, 22, gets at another concept. If p of x equals 0 is a polynomial equation with real coefficients and the complex number a plus bi, where b is not equal to 0, in other words, it has an imaginary part, is a root of p, then what is also a root? All right, complex roots always come in pairs, and they always come in something called conjugate pairs. All right, they never come as a single. They always come in pairs. So you will never have just one imaginary root. You never have 3 imaginary roots. You're always going to have an even number of imaginary roots. They come in pairs, and they come in conjugate pairs. So if a plus bi is a root, then a minus bi is also a root. So if you had 3 plus 2i, you'd also have 3 minus 2i. If you had negative 5 minus i, you'd also have negative 5 plus i as a root. They always come in those conjugate pairs. All right, here we're told to state the degree. The degree is the highest exponent, so the degree is 8. All right, and then we're also told to find all of the real and imaginary roots of the equation. Well, this guy can be easily solved by factoring out the GCF. The GCF here would be x to the 6th. And then I'm left with x to the 2nd minus 9. And then x to the 2nd minus 9 could either be solved using the square root method, or I could factor it as a difference of squares. X plus 3, x minus 3. So now what I have is I have x to the 6th equals 0. I have x plus 3 equals 0 and x minus 3 equals 0. So I have x, if I take the 6th root of both sides here, 6th root of 0 is just 0. And here I get -3 and +3 as the other answer. So 0 and plus or minus 3. But now you know I'm supposed to have 8 8 total roots. Well, the 0, 0 itself occurs 6 times. So in that case, this one doesn't count for just 1, it counts for 6. So the fact that it counts for 6, and then I have another one that's a 3 and another one's a -3, that means I have 8 total zeros that way. It wants me to state the multiplicity. So the multiplicity of the 0, the root 0 is 6. The multiplicity of 3 is 1. The multiplicity of -3 is also 1, because they only occur once. This one should be simple. I'm just doing multiplicity again. This one would give me a root, if I set this equal to 0, of 6/5, and that multiplicity would be 4. This one would give me -1/2, and its multiplicity would be 6. All right, this question, number 25, is giving me the roots, and it's telling me to find the polynomial that has those roots. There's a pretty simple way to do this. You just turn the roots into factors. So x equals -2 would turn into the factor x plus 2. X equals 7 would turn into the factor x minus 7. Then it does not want me to have it in factor form, I don't think. It wants me to type the expression not as factored. So I think I need to FOIL this out. So that's going to be x squared minus 7x plus 2x, so that's minus 5x minus 14. So that should be the answer to that problem. All right, now we're doing something similar. We're told to find an equation with these roots, 10i and -10i. So what we do is we turn those into factors. That's going to be x minus 10i and x plus 10i. And we FOIL. What we get is we get x squared plus 10ix minus 10ix minus 100i squared. And what happens to the 10ix and minus 10ix? They cancel. So now and also remember that I squared is -1. I think we went over that in class, but I squared is -1. So if I squared is really -1, then -100 I squared is really -100 times -1. So that's really just plus 100. So that polynomial is just x squared plus 100. All right, for this one, same thing. We turn it into a factor, but this is going to be a little bit more complicated. So -1, that's simple. That's just going to be x plus 1 as a factor. 2 minus 5i. To make that into a factor, I'm going to say x minus, but I got to subtract the whole thing, x minus 2 minus 5i. So notice I put that in parentheses so that I could subtract the whole expression. And also remember that these complex zeros always come in conjugate pairs. So this problem expects you to know that. It expects you to know that there's also going to be a factor that is x minus 2 plus 5i. Now I'm going to distribute these negatives. So that's just going to be x minus 2 plus 5i. That's going to be x minus 2 minus 5i after I distribute those negatives into the parentheses. And now I have to do some distributing. Okay, so I've got to distribute. I'm going to go ahead and distribute these two expressions with one another. So it's going to be a lot of distributing. X times x, x times -2, x times -5i. That's going to be, it's going to be x squared minus 2x minus 5ix. Then I'm distributing the -2. -2 times x, -2 times -2, -2 times -5i. So that's going to be minus 2x plus 4 minus 10i. Or is it plus 10? It's plus 10i, isn't it? Plus 10i. Yeah. Now I'm distributing the 5i to all three of these as well. It's going to be plus 5ix minus 10i minus 25i squared. Whew. Okay, remember that I squared, what is that? That's -1. So minus 25i squared is just going to be really plus 25. All right, so what happens here? -5ix and plus 5ix cancel. Positive 10i and negative 10i cancel. So this is always going to happen. Whenever you distribute these, all of your terms that have an imaginary part in them are going to cancel out. They're going to go away. So now what do we have? We have x squared. I got minus 2x minus 2x. So that's minus 4x. I got plus 4 and I got plus 25. So plus 29. Then one more little bit of distributive property coming up. I also have to distribute the x plus 1 with that to finish. And that's going to be x cubed minus 4x squared plus 29x plus x squared minus 4x plus 29. And let's see if I can combine terms. X cubed minus 3x squared plus 25x plus 29. So that's what I get when I combine all the negative 4x squared with the positive x squared, the 29x with the negative 4x. This is my final answer. This is the polynomial equation that produces those given roots. Back to solving a polynomial. I want to show you this one because this is one you can actually solve by factoring. It's a kind of factoring called factor by grouping, and it can come in handy sometimes. Now you can also solve it in the app, and that's fine, but I do want to show you how to do this. Factor by grouping is when you have 4 terms. And what you do is you group those 4 terms. You group those 4 terms into 2 groups. So we split the 4 terms up into 2 groups of 2. And we factor out the GCF from each group. So what's the GCF from this first group? It is n squared. I factor out an n squared, and that leaves me with n minus 2 for that group. Here, I don't have a GCF really. But if your first term is negative, you always at least want to factor out that negative. And if you can factor out a negative GCF, go ahead and factor out the negative GCF. I'm just going to factor out a -1 here. And what does that do here? It changes these signs. This becomes a positive n, and that becomes a -2. Now what happens is, think of this as one big term and this as one big term. And what do they have in common? Those big terms now have the n minus 2 in common, so that the n minus 2 is now kind of like the new GCF. I'm going to factor out n minus 2 from that expression. When I factor n minus 2 out of this part, I'm left with n squared. When I factor n minus 2 out of the second part, I'm left with -1. And so this is a good factorization of that original 4-term polynomial. This is how you factor by grouping. I can actually do some more here because this part right here is a difference of squares that can factor more. So the final factorization will be n minus 2, n plus 1, n minus 1. And so my solutions are 2 and plus or minus 1, or 2, 1, and negative 1. All right, this one. This is one you could try to do in the app, but the problem is the app is not going to give you answers that are in this radical format. It's going to give you decimals. And then I guess what you could do, since it's multiple choice, is just type out the square root of 3, or type out the square root of 3 divided by 3 and see what the decimal is and see which one matches what the app tells you. But there's also maybe a more sophisticated way we could do it, and that is to simply do some synthetic division. Let me get it to where I can write on it. 3, 30, negative 1, negative 10. And then we could either put, and we know that since from the multiple choices that either 10 or negative 10 is going to be one of the answers. So I could try 10 outside the box and see if it works, and I could try negative 10 outside the box and see which one works. I've already done it. Negative 10 works. Add down, multiply across, add down, multiply across, add down, multiply across, add down. So what are we left with? Remember, this is going to start one less degree, so it's going to be, we're left with 3x squared plus 0x minus 1. And then I can solve that quadratic. I can always solve a quadratic by some method that we're really good at. This one, I think I'm going to use the square root method. I'm going to move the 1 over. That gives me 3x squared equals 1. I'm going to divide by 3. So x squared equals 1/3. Take the square root of both sides. X equals plus or minus the square root of 1/3, which is the same thing as the square root of 1 over the square root of 3. The square root of 1 is just 1, so 1 over the square root of 3. And then we don't like to have radicals in the denominator, so we have to rationalize that denominator by multiplying that square root of 3 with itself and doing the same thing on top that I do at the bottom. So that's plus or minus the square root of 3 over the square root of 3 times the square root of 3 is 3. So then my answer is negative 10 and positive root 3 over 3 and negative root 3 over 3. So it looks like B is the right answer here. All right, let's look at this one, number 31. We have to find all the solutions to this. If we weren't having to find all the both real and imaginary solutions, we could just kind of use algebra skills and say move the 16 over, a to the 4th equals 6. And then we take the 4th root of both sides, and we say a equals, when we take an even numbered root of both sides, we always have to put plus or minus. An odd numbered root you don't, but an even numbered root like a 4th root or a 6th root or a square root you do. The 4th root of 16, we're trying to figure out what multiplies with itself, kind of 4 of them put together, 4 of the same thing multiplying together gives you 16, and that is 2. 2 times 2 times 2 times 2 is 16, so it's 2. A equals plus or minus 2, but that only gives us 2 solutions. And how many are we supposed to have total? We're supposed to have 4 total if we're going to find the real and imaginary ones. So how do we find the imaginary ones? You could try to do it in the app, and that's fine. The app may do it for you. It may do everything you need. But I'm going to show you another way to do it without the app as well. And I'm going to do it with synthetic division. The rational root theorem. So what am I putting inside the box? I'm putting 1 as the coefficient to the a to the 4th, but then I have to have several placeholders. I don't have an a cubed, I don't have an a squared, I don't have an a. That means I got to have 3 placeholders. A 0 for the a cubed, a 0 for the a squared, a 0 for the a, and then finally the negative 16. And then what do I put outside the box? I already know that 2 or -2, both of those would work because I've already solved that part. So I know that's going to work. So let's go through the process. 1, 2, 2, 4, 4, 8, 8, 16, 0. Got to end up with 0 there. If I don't, then I've done something wrong because I already knew 2 was supposed to work. 2 is one of the answers, so I have to come out with 0 if I'm doing it right. So then what are we left with? We're left with x to the third plus 2x squared plus 4x plus 8. Now we have a choice. One choice would be to do synthetic division again with 1, 2, 4, 8. And then -2 would work outside the box next. And then that would get it down to a quadratic. And then I can solve that quadratic, by the methods we've already discussed. But another way I could do this without doing that is to use factor by grouping. I can tell this one will work with factor by grouping. Not all of them will, but this one will. I can tell because 1 and 2, like 1 times 2 is 2 and 4 times 2 is 8, they kind of both, the groups function the same way. They're both factors. The second term is the same factor as the first term. So factor out the GCF from the first group, that's an x squared, and that leaves me with x plus 2. Factor out the GCF from the second group, that's going to be a 4. That leaves me with x plus 2. And see, factor by grouping has to have these two parentheses become the same thing in order to work. And they do. So then I factor out that x plus 2, that's the same thing, and it leaves me with x squared plus 4. And so then I get x equals -2 from that one. I've already got the positive 2 from that one. Then I got to say x squared plus 4 equals 0 here. Subtract 4 from both sides. So now x squared equals -4. Square root both sides. And what's that give me? X equals plus or minus. Square root of -4 is 2i. So my answers are 2, -2, 2i, and -2i. And now the video is going pretty long. I think it's a little over an hour already. So I'm going to stop it right here for this video. That should help you to complete all the problems from 11 through 31. And in the next video, we will jump on problem 32 and see how far we get with that. Good luck.